This is the first lecture in our Chapter 5 Modern Chemistry book, and we're going to be talking about the history of the periodic table and some of the patterns and trends that we see within the table. So to begin, we're going to start by going back to about the 1850s and 1860. A gentleman named Cannizzaro came up with a pretty reliable way to measure relative atomic mass. We can talk about it more in person, but essentially he decided to use oxygen as a standard to compare to because oxygen was so prevalent and formed so many compounds with so many other elements. And he chose the number 16 as oxygen's relative atomic mass because it was the only whole number that allowed him to still have a whole number for the mass of hydrogen when he compared the two together. And again, there have been lots of changes to that. Well, not lots. There have been some changes to that system in the 150 plus years that have passed, but it was a very reliable and workable system at the time, and it was used by a consortium of chemists, one of whom was a gentleman named Dmitri Mendeleev, who was working in Russia at the time. He was actually a teacher. He was trying to figure out a way to organize the known elements at that point in a way that made it easy for students to work with and for scientists to study. And so what he did is he found that by using their atomic mass, so this is a little different than what we do now. As he used the atomic mass, he found that there were all kinds of trends that occurred, what he called periodically. They happened at predictable set patterns. There was another gentleman also working on a periodic table at that point. His name was Bacher. He was also a teacher, and I believe he was working in Germany. He came up with essentially the same periodic table as Mendeleev, and they had no idea the other was working on it at the same time. For some reason, Mendeleev gets a lot of the credit, though. He published his table in 1869, and what he came up with allowed for properties of elements that were similar to overlap, and he also, really interestingly, was able to predict where elements that were as yet undiscovered would eventually be found and placed. And three of those elements were scandium, gallium, and germanium, which were discovered shortly thereafter. In the couple of decades after the publication of Mendeleev's periodic table, a gentleman named Moseley, who was, I believe, a British scientist, was working with metals primarily. And after experimentation with dozens of different kinds of metals, he found that it made a little bit more sense to arrange the elements by increasing number of protons, so by atomic number rather than by atomic mass. And when he did that, and he did a little bit of restructuring of the table, he found that there were even more patterns and even more overlap in chemical properties. And that led to the formation of the periodic law, which you see here. And that just says that the physical and chemical properties of an element or a group of elements are due to their atomic numbers. The atomic number leads to the properties that we see. In the 100 or so years since the periodic law was created, there have been more than 40 elements discovered, and in each case, the pattern and trends hold true. So elements in the same groups have similar properties, and elements within the same period, which we'll talk more about as we go forward. So backtracking just a little bit, one thing that was not present in Mendeleev's periodic table were the noble gases. He had none of the noble gases included in his table because most of them hadn't been discovered in any capacity at that point. In the mid-1890s, two gentlemen named Rayleigh and Ramsay, this is actually Lord Rayleigh. It's not his given name, but it's his title. They were working in Britain. They discovered argon, and they decided to place argon into a group with helium, which was an already known element, but it hadn't been classified yet. So the reason they did that was because argon is very, very unreactive which is also true of helium. So over the next few years, a bunch of other unreactive gases were discovered. Krypton was discovered, xenon was discovered, and radon was discovered. And because of their lack of reactivity, they were all placed into the same group as argon and helium. And today we call that group the noble gases. And you have seen it all the way on the right side of the periodic table in group 17. The other two groups that are kind of exceptional, I guess, in terms of the periodic table are the two that are found kind of below the main table itself. These are the Lanthanides and the Actinides, and they actually are found within existing periods, but they are placed in separate rows below the table because they have similar properties to one another that are less similar to the other metals and other elements in those groups. But primarily it's because their electron shells fill in a completely different pattern than all the other elements on the table. And so they've been grouped kind of off there on their own, but with other elements of similar electron patterns. So going back to what Mendeleev said about the periodic repetition of properties and characteristics, there are a couple of different ways we can look at this. As we compare elements within a group, so we're going vertically at this point, we can see that there are trends in atomic number as well as properties common to the group. And we'll talk more about those properties in just a minute as we get to the groups themselves. There's also a numeric periodic nature to the table. The difference in atomic number between the first and second elements in a group, is 8. There are 8 protons in difference. As we go from the second to the third, there are also 8 proton difference. From the third to the fourth, we have 18 is the difference in atomic number. From the fourth to the fifth, we again see 18. And from the fifth to the sixth is 32. That pattern has to do with the arrangement of the electrons. And you'll see this numeric trend, 8, 8, 18, 18, 32, come up over and over again. We can see this 8, 8, 18, 18, 32 pattern continue as we look at the number of elements in each period of the table. The one that's slightly different is period 1, so just hydrogen and helium. That group that period, only has 2 elements. Period 2, however, has 8. Period 3 also has 8. Period 4 has 18. Period 5 has 18. And period 6 has 32. So you can see that pattern continues as we go along. Another interesting thing about the periods within the table is that it allows us to sort the periodic table into the 4 blocks that exist within orbital sublevels. So my apologies for the text overlap here. I'm not too sure what happened with my font conversion, but the S block is groups 1 and 2. So the first 2 groups on the left side of the periodic table, the first 2 columns, fill the S block of orbitals. The P block, we're going to go like this. P block fills up groups 13 through 17. The D block fills groups 3 through 12. And then the F block contains the lanthanides and the actinides. So we can split the table up into 4 parts based on which orbitals are being filled by those elements, which makes it super easy for doing electron configurations and predictions of behavior and properties as we move forward. So now we're going to look a little bit at the groups within the periodic table and some of the properties that they share, because we've talked quite a lot about the overlap in properties. So group 1 is the alkali metals, and this starts with hydrogen at the top. Hydrogen is not an alkali metal. It is an exception, but it's in group 1 because it has just 1 electron in the s orbital. Everything else in group 1 is an alkali metal. They're soft and silvery, and they are super highly, extremely reactive, both in air and in water. As we move down the table from top to bottom, the melting point gradually decreases, so it gets easier and easier and easier to melt them at lower temperatures. Excuse me. Group 2 is called the alkaline earth metals, and all of the elements in group 2 have 2 electrons in the that should be an S, in the S sublevel. So their electron configuration would be things like 1s2 or 2s2, etc., downward and downward. They are all hard, dense, very strong metals. They're also quite shiny in many cases. You can see between lithium and magnesium, you've got some good luster happening there. They have higher melting points, and they are very reactive, although not as reactive as the group 1 metals. Then we are going to look really quickly at a couple of the exceptions. So I mentioned hydrogen and the fact that it's grouped because of its electron. Helium also has 2 electrons in an S sublevel, right? 1s2 describes helium. But it is organized with the noble gases rather than with the group 2 metals because it is so unreactive and so stable, just like all of the other noble gases. It's also not a metallic, it's a gas. And so it's a non-metal gas. And so it has more in common with the noble gases really than it does with the metals, and so that's why it got grouped over there. Okay, we're going to skip the P block for just a minute and talk about the D block. So if we're moving from the left to the right on the periodic table, we're now getting into group 3 and going all the way through that big rectangular block up until group 12. These are called the transition metals. And the elements in here, there are a couple of exceptions. You saw these in the last chapter. Chromium was one. I think copper is another one. They have some slight variations in outer electron configuration. However, they are filling the D block, and the sum of their outermost electrons, their outer shell electrons, is always equal to the group number that they are in. So if they have 2 electrons in the outer energy shell that are in the D block and 1 in the P block or whatever, those 1 plus 2 will equal 3, so it will be a group 3 element. Other things that the transition metals have in common is they're very typically metallic. They're what we think of when you think of a metal like gold or silver. They conduct heat and electricity well. They're lustrous, which means shiny, and they are significantly less reactive than group 1 and 2 metals. However, they do have some reactivity, but because they are more stable, they can be found much more easily as pure substances rather than in compounds. Okay, so now we're going to talk about the P block. We're over on the right-hand side of the table, and we're looking at elements groups 13 through 18, where the P sublevel fills up 1 electron at a time for a maximum of 6. When we get up to 6 electrons, we have reached the noble gases, and that's the far right-hand side of the periodic table. The outer level electrons can be found by subtracting 10 from the group number. So if you take 10 from group 3, all of the elements in group 3 have 3 outer electrons. 10 from group 14, they all have 4 outer electrons, etc. The big difference with the P block compared to the S and the D is that there are huge variations in property. The reason for that is we have 3 different kinds of elements happening all within the P block. There are some metals down kind of at the bottom of the P block, bordering on the transition metals, and they have fairly moderate reactivity, which means we typically find them in compounds, but they can be pure as well. There are the metalloids, which is that little stair-step group of elements that comes down, starting at group 14, I believe, or 13 maybe, and it progresses toward the right-hand side of the table. The metalloids are solid, and they conduct heat and electricity moderately well, which makes them sort of like metals, but they're very brittle, which makes them highly unlike metals. And then we have group 17 and group 18, and a little bit of some other elements up in this area, like oxygen and nitrogen, for example. They are all nonmetals. One of the specific groups of nonmetals is the halogens, which are found in group 17. They're right alongside the noble gases. And they are super, super, super highly reactive. They're like the opposite to groups 1 and 2 in terms of properties, but they are super reactive, so they often form what are called salts with the group 1 and 2 elements. You'll find chlorine in this group, for example, and over here in group 1 is sodium, and that's probably the most commonly recognized salt, NaCl or table salt. So then our last two groups are within the F block. These are the lanthanides and the actinides. And again, they are found between groups 3 and 4. And those two little columns, or those two rows, are pulled out and placed below the periodic table. The lanthanides exist within period 6 as well. So if we were going horizontally across the table, they would slide right into period 6. The lanthanides all fill the 4F sublevel. And in terms of properties, they're actually very similar to the group 2 metals. They're shiny, they're dense, they're hard, and they are moderately reactive. Then the last group are the actinides. Again, they are sliced out from between groups 3 and 4, and they exist horizontally within period 7. The 5F sublevel is being filled within the actinide group. Something very interesting about the actinides that we haven't seen or talked about yet is that they are all radioactive. And there are several man-made elements here. I believe there were only 4 naturally occurring actinides. I could be wrong on that number, but the rest of the group are man-made. So that gets us to the end of our brief look at the history of the periodic table and the classifications that we now use. So please bring 3 questions for discussion in your notes, and we will talk more when I see you next. Thanks.